All right, welcome back. So now we're going to start talking about query language to query the databases that we've built. Uh, the query language that we're going to use is an algebraic query language. It's called Relational Algebra, and it's something that you simply need to understand. Even though you're not likely to use it on a daily basis, you need to be able to understand for interacting with databases. If for no other reason, when you ask a database, hey, I submitted this query, but it's taken a really long time. What exactly are you doing? What it will do is it will talk back to you in relational algebra. So it will say, oh, this is what I'm doing, and give you a relational algebra expression, which you should then be able to understand and go, that's not at all what I want you to do. And that's the way that you improve your performance. Okay. Now, I want to talk a little bit about what we mean by algebra. Okay. So here's the high school algebra. So we have x plus 25y minus xy cubed divided by 5. That's an algebra expression, okay? And there's two things that it says. It tells you, okay, if we have value of x and y, then this is the value that I want you to return, okay? But more than that, it also tells us how it wants us to compute that value. So in this case, for example, we would say, oh, the way that you should do this is multiply y by 25 and take the result of that and add it to x. Okay, and then what I want you to do is take the value of y and raise it to the third power, take the result of that, multiply by x, and divide the result of that by 5. And then we'll take the result from step 2, right, which is x plus 25y, and subtract what we just got from that. Okay, so not only are we saying what we want, we're also saying how to do it. May not be something you've thought about much, but that's what we call an imperative language. Okay, algebra is an imperative thing because it tells you what to do and how to do it. Okay, now there's an alternative. Okay, and that's what I say. You may not have thought about it much because when you program, you're doing that, right? You know, if you're writing Java or C# or JavaScript, you're saying how you want to accomplish whatever goal you have in mind. Okay, to give you an example of something that doesn't go like that, that would be like CSS in to build a web page. So the HTML tells you what should be there. You know, here's the heading that has a title like imperative versus declarative. Here is a list, and here are the bullet items and so on. And with CSS, you can say, oh, I like my headings to be in a font that is 24 points, and I want it to be in this color, and I want it to be centered, or whatever it is that you want. But you don't actually say how that should happen. You're simply saying what you want to be there. That is declarative programming. Sometimes we get away with it. I love declarative programming. And quite frankly, most of the time we don't. We have to do imperative stuff. But databases use declarative query languages. So as a programmer, you get to say what you want. Let the computer figure out how to achieve that. Okay? So a database system is very good at coming up with good execution plans. That's the how part. Okay? And what I mean by good, I mean orders of magnitude better than what you would have done on your own. And I am not kidding. Okay? Because it's very hard to do even simple things like sorting the elements of a file. Now, if you're thinking to yourself, I know how to sort, that's easy because it's in memory. That's why it's easy. Okay, if you have it in memory, yeah. Quick sort, bubble sort if you must, insertion sort if you really must. Fine, trivial. Okay. When your file is too big to fit in memory, when you actually have to split it into sections, load them, merge them, put them back out, read temporary files, and so on, that's complicated. But it's very easy to say in SQL, order by this. Okay. So, I guess I can even go further than that. Okay, the best execution plan depends on the characteristics of the data. Okay, so it's not just that it's really difficult, which it is. Okay, it's that there might be choices. Oh, should I do this? Like for example, should I sort this file first and then try to process against that one, or should I just go ahead and read them and not worry about ordering? Okay, and do that later. If you do it for very large files, sorting might make a significant difference because the time component there might be n log n as opposed to n squared. Okay, but if you can read one of those files in memory, then maybe it doesn't help. It might end up being order n instead of order n log n. And so we're happy not to sort. We would have wasted that log n component. It just depends on how I'm storing the data on disk and precisely how large that data is. So it might even change over time as more records are added. So you as a programmer would not even have enough information to do the right thing. Okay, so we're going to leave it to the database system to figure out the best thing. And when it figures it out, it will take whatever you said, which is the what you want, and it will turn it into relational algebra. Okay, so let's talk about relational algebra expressions. If you look at high school algebra, okay, then expressions are trees, right? I mean, you don't think about it that way in high school, but we're computer scientists. So these are trees, and the leaves are actually either numbers, constants, or letters representing variables, and the internal nodes are operators like plus and minus and times. So what does a relational algebra expression look like? Well, again, it's a tree, and the leaves can be either variables, and the variables now are actually stand for relations. So a variable could be movies, okay? Or it could be a constant, which is a very specific relation instance. We will rarely use constants, but that would be like actually enumerating the, that would be like enumerating what we want a relation to have, okay? All right, so the internal nodes are relational operators, and you're going to have to learn a few of those. So the first relational operators, or the first kind of relational operators, are just set operators. Remember, relations are sets of tuples. So it makes sense, since they're sets, that I can do things like unions and intersections, set difference, and even the Cartesian product. Okay, those are all kind of reasonable things to do with sets. The rest of these are more databasey. Okay, so one of those is called selections. And what selections does is it says, okay, so here's a table that has 13,000 rows. Those 13,000 rows might be, for example, the students at the University of Wyoming. And I want to filter those students by, for instance, only the ones who are computer science majors. Okay, so now you end up with 250, 300 out of those 13,000. That's a selection. So it lets me look at only some of the rows. Okay, a projection, and the name projection actually comes from mathematics, where you're taking a three-dimensional tuple and projecting it onto a two-dimensional plane. So a projection lets you filter out columns. Instead of 3 columns, I now have 2 columns. Okay, so I have selections. I only want some of the rows. I have projections. I only want some of the columns. There's also a fancy thing called join. Okay, we're going to talk about join later. This is the most important relational algebra operator. And what it is really is a combination of cross product and selection. Okay, and then there's rename. I know what you're thinking. Rename, that is the lamest operator ever. Well, maybe, but actually there's a lot of things that you can't say if you're not allowed to rename the columns or tables, and you'll see why shortly. Okay, so let's just deal with the set operations and be done with those. So set operations are written as R union S, intersect S, R minus S, R cross product S. You would simply do this. Normally, the only difference is R minus S. You may use a backslash for set difference, but other than that, you already knew this. Okay, that's just discrete math, right? Of course, just as in discrete math, you can nest these operations, so I can have the union of R and the intersection of S and T. Okay, so we can do that, and you can imagine that you can nest this as deeply as your heart desires. One restriction is that whenever you do the union of 2 tables, what we expect the result to be is another table. Okay, so in regular algebra, you don't really worry about this because all the leaves are just numbers, right? Whether it's a variable or a constant, it's still just a number. So when you add them, you get a number, multiply them, you get a number, and so on. So any node just has a number. But it's different for relational algebra, because this table might have a name, a title, a length, a year, and a genre, but this other table has a name and a birth date and an address. Okay, so if I simply combine them using union, what I would end up is a bunch of rows, but not all the rows will be of the same type, okay? So that's not a legal table, because we said that for a table, all of the rows had the exact same attributes, okay? So, so the way that we get around this is by saying you're only allowed to take the union of tables that are, quote, union compatible, okay? And what does union compatible means? They have the same attributes and domains, and they have them in the same order. That last one we can relax a little bit, okay? But we'll just leave it, okay? Same attributes, same domains, same order, okay? And by the way, that is not just for union. I mean, the technical term is union compatible, but we say that when you take intersection, they must be union compatible. When we do set difference, they must be union compatible. This does not apply to cross product, okay? Because when you take the cross product, you get all of this row and then all of the other row. They don't have to be of the same kind, okay? So here are some examples. We have two relations, and we're about to do unions and intersections and such. The thing that I want you to notice is that these are union compatible. Name, address, gender, birth date, name, address, gender, birth date, okay? And we have this row, which happens to be in both, and then we have Mark Hamill here and Harrison Ford there. So Carrie is the only one who is in both relations. So union, that's easy. That's Carrie Fisher, Mark Hamill, Harrison Ford, okay? I end up with 3 tuples, even though each relation had 2 tuples each. That's because one of them was in common. You shouldn't be surprised by this, okay? And then we have intersection. The only one that's in both is Carrie Fisher, okay? Set difference. We take R minus S. Then we had Mark Hamill in R, but not in S, so that's the only thing that remains. S minus R, we have Harrison Ford in S, but not in R, so that's the only tuple that remains. Again, this shouldn't surprise you because that's just the way set difference works. Okay? Cross product, okay? This is one that has a few surprises. What we're going to do is we're going to build a new table that has the attributes from the first relation and then the attributes from the second relation, okay? Now, this is a strange example because the tables are union compatible, so they have the same attribute names. Because of that, you have 2 address, 2 name, and so on. The way that's differentiated is we append the table name dot and then the attribute name. That's the new attribute names. If I had chosen non-union compatible tables, then there's no need to do that, and databases will just not do it if they don't have to, okay? Now, how do we actually build them? Let's look at this one here. This is just a tuple from the first table, and then this is a tuple from the second table, and then the second tuple from the first table. So look at this. Carrie Fisher is our first row in R. It will appear twice because it appears once for each tuple in S. Likewise, Mark Hamill was our second tuple in R, and it appears twice because it appears once for each row in S. Okay, so there's just kind of an order in which we do this. Okay. By the way, there's a note here that I didn't mention, but I want to call explicit attention to it. I told you earlier that renaming was cool. Okay, and I know you were thinking this is a really lame operator. Well, here's an example of where renaming is super cool. Instead of just letting the database come up with R dot and S dot for us, we could have named those attributes ahead of time, and then we wouldn't have needed to do the table disambiguation rules. I'll try to convince you more later. Okay, so let's do projections. This is actual a database C operation. Okay, so a projection lets you choose which are the columns that you want to see in the result. Okay, and the way that we denote this is by the Greek letter pi. This is simply because if they used the lowercase p, nobody would have been impressed. But when you make it a Greek letter, then it has more gravitas. So pi for projection. Pi is just Greek p. Now, you need to specify what columns you want to keep, and the way you do that is by just listing them as a subscript of pi, and then just put parentheses and put in there whatever expression you're taking a projection of. So here is projection pi, title length year of movies. Okay, so we just got rid of genre. Okay, as always, you can nest thing. So here's a projection of A and B, which are attribute names of R cross product S. Okay, remember that example. All right, so here are some simple examples. This is our old friend, the movies table, and we use pi, projection, title, length, year, and so the result is title, length, year. I noticed that we lost the column here, genre, okay? By the way, we also changed the ordering of the columns. Just snuck that in there. Here's another example. This time we're going to project the genre. So if you look at this column here, genre, you see drama, sci-fi, and sci-fi. When we actually do a projection, we end up with drama and just sci-fi. We don't have it twice because the result of all of these operations is a table, and tables don't have duplicates. Okay, there are no duplicate rows. So we just got rid of one of those. All right, selections. Again, this is a very databasey thing. So with selections, what we want to do is we want to have only some of the rows. And how do we do it? Greek letter for selection, that would be sigma. So lowercase sigma, and then we have to specify the condition. What rows do you want? And we just put that as a subscript. I don't know who came up with that idea, but that's the way it's done. And then parentheses, and then whatever relation we're doing this of. So for example, sigma, or selection, year equals 1977 of movies, will return all the movies that were released in 1977. That's it, okay? As always, we can nest sigma a greater than 10 of r cross s, okay? We will be coming back to that. Okay, so here's an example. Sigma, selection, of year greater than or equal to 1975 of movies, we get two movies, Star Wars and The Matrix. Sorry, Wayne's World, I like The Matrix better. Okay, here is another condition. Length is greater than or equal to 130 and genre is sci-fi. So now we're looking at very long science fiction movies. Notice that I can use Boolean relations and, or, not, parentheses, all that stuff in the condition. And the only one that passes this particular relation instance is The Matrix. All right. So now comes the most databasey operator of all, and that is the joins, okay? So the first thing I'm going to show you is what's known as a natural join. And a join it's actually nothing new. A join is simply a combination of a cross product, which we know how to do, and a selection that we know how to do. So let's look at these two tables, okay? So movies has a title, a year, length, genre, name, and producer certificate number, okay? And studios has a name, an address, and a president certificate number. Now, the one thing that we changed is that in the original schema, this name was actually studio name. And there was a good reason for that. If you saw name, you might be tempted to think it's the name of the movie, right? It's not. That would be title. So name of what? Don't ever let somebody wonder that. Let them know the studio name, okay? But we renamed it to name for this example only, so keep that in mind. Okay, so what I'd like to do is figure out what studio makes each movie. That's what a join can do, okay? We're actually going to do it first as a combination of a selection and a cross product. So we'll take movies and studios and we take the cross product. So what does that look like? Each movie is listed with 1, 2, 3, 4, 5, however many studios. Then the next movie, 1, 2, 3, 4, 5, however many studios, and so on, right? Now, to that gigantic table, we're going to select only the rows where the name in movies is the same as the name in studios. That's what this does. Movies.name equals studios.name. And so we're left with the rows that actually correspond. So yeah, that is the studio that made that movie. Okay. So let's actually build it. Okay. So here is movies. Title, year, length, genre, name, producer, certificate number. We have 3 of those. The studios, again, we have 3 studios. Okay. So step 1. This is very important. Okay, guys. Step 1, movies, cross product, studios. So what do we get? Title, year, length, genre, movies.name. Okay, because there's duplicates. Producer certificate number, studios.name, address, and president certificate number. Notice that these last 3 come from studios. The first 1, 2, 3, 4, 5, 6 attributes come from movies, okay? This is just a cross product. So here's the first row of movies, and then 1, 2, 3 rows from the studios. This second row of movies, 1, 2, 3 rows from the studios, and we actually ran out of room, so you only see 2, but there's 3 times 3, 9 rows in the cross product, which you should know from 2300. Okay, so now let's add the selection. So the selection is that movies.name is equal to studios.name. MGM is here, Lucasfilm, Warner Studios. Okay, this particular example, the studios are unique. In general, there wouldn't be because, you know, like Lucasfilm actually made more than one movie. I think they're all Star Wars movies, but still, they made more than one of them. All right, so now we're going to do it with a join. Movies join studios, well, that's just the same that we had before. The only thing that we do different is you see right here is movies.name and studios.name, and you can see that they're the same. They're the same because of the condition on the selection, right? So we will now just say name and get rid of the other one. Actually, I should have gotten rid of studios.name. I'm sorry. That's what a join is, okay? A join is just a shorthand for a selection of a cross product. So we take the cross product and then we just get rid of all the rows that we do not want, okay? A natural join, what makes it natural is that the condition that we're joining in is implied, okay? Is totally implicit. You don't have to say what the condition is. The condition is just simply, if you see two attributes with the same name, make sure that their values are the same. So name and name, that's why I changed it from studio name to name. Well, it's got to be MGM, okay? It's got to be Lucasfilm. I mean, you know, it's got to be the same one. All right. Okay, so having done that, let's look at something else called a theta join, okay? A theta join just simply allows an arbitrary condition. It doesn't have to be attribute names are the same, okay? It can be anything you want, okay? So with a theta join, you actually give the condition as a subscript of the join operator, okay? And the join operator is a bow tie. I do not know why it's a bow tie, but as a Whovian, I can tell you that bow ties are cool. So as a database person, you gotta love bow ties because joins are the best relational operator. So right here, we're gonna join movies and studios, and we're gonna join it on the condition studio name. We're back to the original schema, equals name. The result is going to be the exact same as before, okay? All right, we've talked about joins. I cannot overemphasize the importance of joins. If you're thinking, yeah, we're never gonna see those again, you're wrong. We're gonna see them all the time, particularly in the exams, okay? So make sure that you really learn how to do joins. The homework will help you, okay? But before I set you loose on that, I just want to mention a few things that I hope you can really kind of internalize about joins. So I call this little join lessons, okay? So let's start with a simple one. Suppose that I have a table called S that has M as in Mary rows and R that has N as in Nancy rows, okay? Then if I take the cross product, this is just discrete structures, 2300. If I take the cross product of S and R, then I end up with exactly M times N rows, okay? Sure, I'm sure we can believe that. So what about the join of S and R? You know what? There's a lot of possibilities. It could be 0, okay? For example, it could be 0 if I join them and I say, well, studio name is equal to name, and that never happens, okay? So yeah, it could be 0, right? It could be exactly M or exactly N, and that will happen when exactly one row in R should match one row in S. So for example, for studio names, that should be the case. The result of studio join movies should be the number of movies, right? Because for every movie, there is one studio, okay? So it could be that. It could simply be one of those two numbers, M or N. Or it could be as big as M times N, okay? And that will happen when you take the cross product and then all the rows in the cross product match the selection criteria, okay? So 0, M times N. Think of those as constant, linear, quadratic, okay? So that's a pretty big range of possibilities, okay? What should it be? Depends entirely on your data. So student ID equals enrolled in student ID. That should be linear, right? Because for every enrolled in tuple, there should only be one student because it marks what that student is enrolled in. How about student gender is equal to advisor gender? Well, shoot, that's going to happen half the time, right? So I should end up with m times n divided by 2, or something close to that. So you should just know that the number of tuples depends very much on the characteristics. Typically, what we want it to be is linear. That's what we hope. Okay. All right, join lesson number 2. You really need to figure out how to execute your own join expressions, right? So if I give you a join expression and I give you a couple of relation instances, it is perfectly legitimate for me to ask you, what is R join S, okay? Here's my trick for doing it. By the way, this trick has a name. It's called naive nested loop join, okay? And it's one of the things that programmers will do, but not databases because it's too slow, okay? But it is the fastest way for humans to do it. Here's the way we do it. To do R join S, start with the first row of R, and then immediately go through S and find all the rows that will make it to the join, right? So what we're doing is we're kind of doing the cross product by taking that row of R on all the rows of S, and the selection. We're not going to write all the rows in the cross product, only the ones that are going to match the condition, right? So that's the little shortcut. So we do that for the first row. Then we do it for the second row of R. We write R and all the matches from the cross product. And then we look at this next row of R, all the matches from S, and so on and so on and so forth. So that's the trick that we did before. Okay, another lesson. Databases are really, really, really good at executing joins. In fact, if you look at the database literature, say from the late 80s throughout most of the 90s even, the literature was almost entirely about how do we make joins fast, okay? That's if you wanted to publish, that's what you wrote about, okay? So they spent an awful lot of time of effort in figuring out how to do this. Now let's see how to do it, okay? Let's just try to compute S join S. Why? Because it's easy, okay? So just one table. And S is going to be the table that has all the students at UW. All right, so how large is S? It's about 13,000. That's the number of students at UW, okay? So if we look at S times S, the naive method that says for each row of S, and then inside of that is another loop that says for each row in S, okay, because it's the same table, then you would end up having 13,000 squared operations, okay? That ends up being about 1.7 times 10 to the 8th. 10 to the 8th is a respectable number, right? You know, you're talking what, 100 million? Okay, this would be 170 million. Okay, now each step that we're talking about here is actually a disk access. We go out the disk to grab this row. So even if disk accesses are fast, and I am not an authority on state-of-the-art hard drive speeds, but as far as I can tell, state-of-the-art is somewhere around 1 millisecond, at least for a commercial that I can buy a hard drive. So in that case, we end up with 1.7 times 10 to the 5 seconds. Okay, so what exactly is that? It's about 2,800 minutes, which is about 47 hours, which is nearly 2 days. That's a long time. Okay, that's way longer than you would be willing to wait for the answer to this result. Okay, now in reality, UW's database can probably join those two tables in seconds. Okay, at the most minutes, and I would put money in seconds. Okay. That's why you use the database optimizer. That's what the database optimizer does. And you should never, ever, ever try to implement your own database in your code. Like I've actually seen people write this join by going to the database and saying, give me R, and then for each row in R, issue a second query that tries to get the related tuples in the second table. It's like you're doing naive nested loop join when you could have just given a join to a database and it would have done something much faster. Don't do that. Okay, something else I want to emphasize in this lesson. Naive execution was 2 days. In reality, it would take seconds. Let's say 20 seconds, okay? The query optimizer, what he's doing is going to try to find some kind of execution plan that's a lot closer to the optimal, which is 20 seconds, than to the really stupid idea, which is 2 days, okay? It will not try to find the optimal, okay? So this is an optimizer in name only. It doesn't try to optimize. It simply tries to be not embarrassing, okay? So in here, if the optimal plan takes 20 seconds, and let's say you do it in 30 seconds, that's not so bad, right? Because it could have been 2 days. So I'll take 30 seconds. I'll take 2 minutes, okay? So what he's really doing is just trying to find something that's, close to the optimal, and definitely not as bad as you could do it if you didn't have an optimizer at all. So don't be confused by the word optimizer. Okay, fourth lesson in joins. Here's a little fact. In the third quarter of 2015, Facebook had 1.55 billion active users. Okay, 1.55 billion. That's a hard number. Okay, so let's put it in context. Roughly speaking, that is 120,000 universities the size of UW. Okay, 120,000. Put that in context again. And there's only 4,000 universities in the United States. Okay, and that includes community colleges. So 120,000 is a lot of universities. Here's another way to put it in context. There's about 7 billion people in the world, which means that, 1 out of every 5 uses Facebook at least on a monthly basis. That's pretty amazing because that counts, men, women, children, really old people, babies, okay? Living in places where there's no internet, right? So, it counts everybody. 1 in 5 is using Facebook regularly. All right, so let's go ahead and try to join Facebook's user table with itself. That ends up taking, roughly speaking, 2.4 times 10 to the 15 seconds. 10 to the 15, that is a big number, okay? That ends up being about 3 times 10 to the 10 days. Wow. It's hard to relate to these numbers. Just how long is that? Okay, that's about 7.6 times 10 to the 7 years. All right? I can start making sense of that. That's actually 76 million years. The dinosaurs were wiped out 65 million years ago. So you would have to have started 11 years before the dinosaurs were wiped out to finish joining Facebook's user table with itself. That's just not going to happen. So conventional wisdom when dealing with large databases is that once you start using joins, you are doomed, okay? You are just not going to be able to do what you want. Now, I don't consider that true, okay? But it's certainly not entirely false. So, it's one of those engineering rules that is true in context, okay? But it definitely explains why Facebook doesn't use a relational database. They use their own database called Cassandra. It's why Google doesn't use relational databases. They use their own database called Bigtable. It's why Amazon doesn't use relational database. They use Dynamo, and so on and so forth. All right, fifth lesson that I want you to learn about joins. Suppose you want to find all movies and their producers. That's what joins are for, right? So we'll join movies on MovieXX, and on the condition producer certificate number is equal to the certificate number. It's similar to stuff we've done before. Now, suppose we want to find all producers. You could just try to do a selection or a projection on MovieXX, but that wouldn't work, right? Because what we want is only the folks who have actually produced the movie. So here's what we'll do. We'll join those two tables, movie and MovieXX, as before to get all of the movies and their producers, and then we'll project so that we only get the information about the producers. So right here, movie and MovieXX are joined, and then we project on the producer name, address, certificate number, and net worth. Neat trick, huh? Make sure you know how to do that. Okay, let's try to find all the producers who have produced more than one movie. Because, if you're just a one-hit wonder, we don't need you, okay? That's not everybody in MovieXX. Only the executives who have produced 2 or more movies. So how do we do that? There's a special trick that you need to know, okay? And the special trick is that we're going to join MovieXX not with movies, but with 2 copies of movies. And here I'm simply calling them Movies 1 and Movies 2. So we'll join MovieXX with Movies 1 and Movies 2. And when we join, we have to have conditions such that the executive produces Movies 1 and produces Movies 2. Okay, that's trivial. I'm sure you can do that. And we also have to have a rule that says, oh, and by the way, Movies 1 and Movies 2 are different, so that we don't just say, yep, George Lucas produced Star Wars 1977 and Star Wars 1977, okay? Let's try something else. Let's try to find all the movies and the movie stars that are in them. It's actually relatively straightforward by now, I hope. We're going to take movies and movie stars, and we can't just join those together because they have nothing in common. but we have stars in, which does have something in common. Stars in, each row has a movie and a movie star. So if we join all those three tables, we will actually get the movies and the movie stars in them. You should be able to do that, okay? Let's raise the stakes a little bit. Let's play the Kevin Bacon game. And the Kevin Bacon game revolves around trying to find movies that Kevin Bacon starred in. So let's find all the movie stars in movies that also involve Kevin Bacon. So we're again going to join those three tables, but we're going to do it in the following way. Movies will join with stars in 1, that's one copy of it, and a selection of movie stars 1. These subscripts mean that it's a copy of that table. Okay. So what exactly is this selection of movie stars 1? We're only interested in movies that have Kevin Bacon in them. Okay. So the selection is, and name is Kevin Bacon. All right. So the movie stars that we have here is just one. It's just Kevin Bacon. And we join that with stars in. So we get movies that Kevin Bacon stars in. And then we'll join that with another copy of stars in and movie stars. Okay. And the second copy lets me find all the other people that are also in that movie. Of course, we're thinking about it now. I probably should have selected a movie stars 2 and name is not Kevin Bacon. Okay. So this will actually give us Kevin Bacon, who is in all movies that he starred in. Okay. All right. So here's something you should realize by now. Joins are extremely powerful. Okay. Easily the most powerful relational movie operator. The relational algebra operator. You should know how to use them. And you should let your imagination run wild. So can you join movies with itself? Yes. Should you join movies with itself? Yes. Why not? For example, I want to find all movies that came out in the same year. Okay. Then I'm going to join movies with itself. I want to find all employees that supervise other employees. We'll join the employees table with itself. Okay. So it is a useful trick to have like 2 copies of the same table in a join, so we can compare different rows of the same table at the same time. All right. From there, I'm going to move to renaming. This is the operator that I am now in a position to convince you is really useful. And the reason it's really useful is because remember when we said movies 1, movies 2, movies 3? We were renaming movies. Okay. So one of the things that we often want to do is just rename the relation and leave all the attributes the same. So we do that by saying row for rename, and it's just the name of the movie, right? So row M2, that's the name of the copy, and then here is the table that we're renaming, movies. If you actually want to rename the attributes, then you can do that too. So here we have row M2 is the name of the table, and then parentheses, the attribute names, title, year, length, genre, S name instead of studio name, and prod instead of producer C number, and movies, okay? So it's easy to use, really super powerful. So let me give you an example. Remember we wanted to do something like movie XX join movies 1, join movies 2. So here's what we'll do it to get different movies. Movie XX join, and notice what I'm joining on the condition, M1 producer C number equals certificate number of rename to M1 the table movies, okay? And we'll join that with rename to M2 the table movies. That was the rejoining and the renaming, right? And so here is what we're joining on. Movies 2 producer certificate number is the same as the certificate number, okay? And what we want is for them to be different movies. And here's one way to do that. Maybe they have different titles, in which case they're different movies. Maybe they have different years, in which case they're different movies. And remember that to be the same, they have to have the title and the year. Okay. Look at that expression. That's starting to get a little hard to read. So it is sometimes useful to kind of have a different way of writing linear algebra expressions that is simply easier to read. And the trick is just to let you name expressions and then use that name elsewhere. So here's how we do it. We're going to create a new relation called R that has attributes A, B, and C. Colon equals, that's the assignment operator. And this is just a relational algebra expression, S join T intersect U, all right? And then we can use that elsewhere. So look at this. MM, which is kind of my notation for movies, is the join of the table movies with the table movies. And what I'm joining on is the fact that they have to have the same producer number. Okay. Now, FMM is that result of MM filtered so that the movies are actually different. Okay, so here we have MM, but only when M1 title is not equal to M2 title or the year is not equal to M2 year. This is the filter version. So now the answer that we want is take that expression, which has all pairs of movies with the same producer, but that are actually different movies, and then we'll join that with the movie exec so that we can actually get the name of the executive. Okay. We've seen a lot of relational algebra operators, and I don't blame you for having a little fatigue, okay? But here's some maybe good news, maybe bad news. If you actually use relational algebra rules, you find that you don't need all of them, okay? So, trivial example, we had join. And how do we define join? Always a selection of a cross product, right? Then we don't need join. We could have just stuck with cross products and selections. So, for instance, here are some other such rules. We don't need intersection because intersection is the same as the difference of R and R minus S. You might have to think about that, but that does end up being the intersection. A theta join is just a selection of that theta with the cross product. We talked about that. A natural join becomes the projection over the things that, well, actually the projection over all the columns, right? From the... I'm sorry, let me start over on that one. Okay, so here's what we'll do. We'll take the cross product, and then we'll take a selection, but the selection that we're doing is on the equality of the columns that are equal, right? And then we'll project so that we have one copy of those equal things. We don't want r.y and s.y, okay? So we'll just split that. And then we'll rename it so that it's just x, y, and z instead of x, r.y, and z. It's a little fancier than it needs to be, okay? But the point is that, yeah, we don't need natural joins, okay? If you really work at it, it ends up that all you need is unions, set difference, projections, selections, cross product, and renaming. Actually, you can have other things that by themselves are enough, okay? But it's just so convenient to have a lot of these operators. So, along these lines, there are some things that are just simply always true. If you start thinking in terms of, say, 4100 instead of 2300 in your computer background, then you'll recognize that these are theorems, okay? And one of the theorems says that joining R with the union of S and T is the same as joining R with S and then unioning that with R and T. We actually took advantage of that when we computed joins where we did it one row at a time. We were really doing that. We were breaking up the table into lots of little tables, joining them, and then unioning up the results, okay? Here's another one that should be pretty obvious. If I do a theta join on R and S using the conditions theta 1 and theta 2, okay, then we can actually join them on theta 1 and then do a selection on theta 2. That will also work, okay? There's lots of these. I mean, there are dozens, maybe hundreds of these little rules, and that's a good thing because what it means is that when you say this is what I want, the query optimizer has lots of relational algebra expressions that will get what you want. And so now we can choose between them. Okay, I'm going to finish by talking about constraints, okay? And since we've done all the hard work of relational algebra, constraints are actually pretty easy, okay? So what do we mean by a constraint? We want to limit the possibilities as to what a column is allowed to have. So here we have genre. It needs to be sci-fi, comedy, or drama, okay? We might have the year has to be greater than 1900, right? Lots of little things that allow you to specify this. The thing that you should really understand is that you can always specify a constraint as a query. So if you want a constraint language, really what you need is a query language, which we already have, okay? So we'll use relational algebra to do it. Later, when we use SQL as our query language, we'll use SQL to describe constraints too, okay? So here are formulas for constraints. We have two ways to do it. You could probably come up with more, but these are the two that are often used in databases. The first one is some expression should return nothing, okay? So alpha is equal to empty. What that means is alpha is not allowed, okay? So you use a relational algebra expression to specify the bad things, right? And then that should be empty because there should be no bad things in our database, okay? The other possibility is to say alpha is a subset of beta. What that means is that every single row that has the property alpha must also have the property beta. Okay. Of course, you could get away with having just one of these. Okay. So you could. I mean, you actually don't need to know both, but it's convenient to be aware of both, because when we'll talk about SQL, actually in SQL, you're allowed to specify them using both techniques. Okay, so here's one kind of constraint. It's called a referential integrity constraint. And what this means is that if you have a value that appears in one context in your database, so it's in some cell, that same value must appear in some other context in your database. For example, let's say that you found a person, and that person is in starsin.starname. So if we look at the starsin table, somewhere in there we find Carrie Fisher. Okay, then the constraint that we have is that, oh, that person must also appear in moviestars.name, because you cannot be a movie star unless you actually star in a movie. Okay, so that's what that constraint would say. So more generally, we would write it this way. We'll have a projection, right? The projection of some attribute in some relation, that is, all of the values that appear in that attribute in that relation are a subset of all of the values that appear in some other attribute in some relation. Okay, so that's how we specify that. Well, I could have written it this other way, right? This is the same. If I take the set of all values of A and I take away the set of all B values, I end up with nothing, right? So that's why I said earlier that you can specify all of these constraints in two ways. Sometimes one is easier than the other, so that's why it's good to know both. Okay, so more examples. A star that stars in a movie must actually be a movie star. Okay. If a movie has some producer certificate number, that really needs to be the certificate number of some movie executive. Okay. And if there's a movie that has some stars in it, that movie better exist. That really should be a movie that came out in that year. Okay. So these are all called referential integrity. Okay. Key constraints. We already seen those, right? A key constraint says that no two rows can have the same values in those attributes, right? So let's say that attribute A is a key for relation A and B. Here's how we're going to specify the constraint. We'll take the relation and we'll take the cross product with itself. Of course, we're going to have to rename one of the copies. So now we have A and B1 and also A and B2. Those are two tuples that I found, okay? So if those are two tuples that I found that have the same A, right, because it's AB1, AB2, then actually they have to be the same tuple, because that's what it means to be a key. And since they're the same tuple, that means that B1 is equal to B2. Okay. Another way of saying that is that you cannot find any rows that have the same value of A but different values for B. That's the way we're going to write it. So we'll take R, we'll take the cross product with itself, renaming it to R2, and then we try to find all tuples that have this property. They have the the same value of A and different values of B. What should the result of that be? The empty set, because there should be no such tuples. Okay. So here's an example. This is actually a really nasty thing, right? In fact, it's so nasty it didn't even fit in my slides, right? But you can look at the conditions. M1 title is M2 title, M1 year is M2 year, and length is not equal to length, or genre actually is an and, not equal to genre, and so on, right? So let's bring it over here. We'll start with a cross product. That's just M movies, cross movies, and called it M1 and M2. And now what we're going to say is we're going to look at the key. Okay, so these are all of the, this is just a selection of the cross product where M1 title is the same as M2 title and M1 year is the same as M2 year, right? So I've looked at all tuples that agree on the key. And now let's look at all the tuples that do not agree, right, when you take the key. So I'll take all of the ones that agree on the key, but then I'm going to filter out when they have different lengths or when they have different genres, or basically I'm looking for any differences at all between those tuples that have the same value of the key. And the difference should be empty. There should be no rows that satisfy that, okay? Because that's what it means to be a key. Okay, let's do an easy one because keys are pretty hard. So let's do domain constraint, okay? The domain constraint just simply lets me say these are the only values that are allowed in this attribute. So gender, for example, is a character, right? It could, but that could be any character, right? And there's lots of characters, you know, I, J, K, and so on. But in fact, we're only going to allow M and F. So I can say the selection of movie stars where gender is not equal to M and gender is not equal to F, right? So anything other than those two should be empty, right? That's the kind of thing that a domain constraint might be. So here's a really, really hard example. And this just shows you how powerful these constraints are in databases. So I would like to have a constraint that says that if you are the president of a movie studio, then your net worth has to be at least $10 million. Okay? So here's a simple way of doing it, which doesn't work. And that is select from movie execs people that have less than $10 million net worth. That selection should return empty. The reason you can't do that is because movie execs has lots of executives, not just the president, but it also has the intern that's making, you know, $2 an hour, maybe not even getting paid. So no, you can be a movie exec without being a studio president. We need something different, okay? So how do we limit it to just presidents? Well, here's what we'll do. We'll take studios and we'll join that with movie execs, right? And we'll join it using the president certificate number must be equal to the certificate number. We did that before to get the movies and the movie execs. And now we can say out of that table, the net worth must be greater than or equal to 10 million. So what we do is we take the rows where the net worth is less than that, and that should return the empty set. So I hope you can see just how powerful relational algebra is. It lets us express many, many, many different things, both in the context of queries and in the context of constraints. Now, if you're like me, you've seen it, you appreciate it, and you probably can't do any relational algebra expressions. That takes practice, not listening to me talking about it, okay? So go to the homework and start doing lots and lots of relational algebra problems. That's how you will learn how to use this. All right, good luck. I'll see you all when I come back from my trip. Bye-bye.